There's chronological age, but there's biology of aging, and it actually has a clinical impact. We target aging and we prevent age-related diseases.
What's your longevity protocol for you, Nir? What do you do to keep yourself healthy and everything you know about longevity and aging? We want to know. What's your protocol?
Yeah, so let's start with the obvious. I exercise every day, by the way, which is almost 365 days a year. I missed this week. I was on a plane. I usually don't miss, but exercise. Now, what exercise? Very briefly, Peloton is my to-go-to, but I'm doing other things too. But twice a week, I have a trainer that mostly works on my muscle and flexibility, and I think he's getting me. I'm always trying to maximize it and getting to a better place. But this is the regime. As far as eating, it's mainly intermittent fasting. Okay, I had dinner last night at 7:30. It's already 1:30 here, so I'm 17, 18 hours. And unless I see the podcast and I talked lots of nonsense, I think I'm fine.
You were good.
I feel fine. And that has improved my health tremendously, by the way, including my exercise capacity in a mysterious way. And by the way, again, this is not for everyone. It's better for men than women for some reasons, at least for weight loss. But some people are saying I cannot do it. I get hypoglycemia. They don't. But anyhow, it's not for everyone, but it's really great.
If you're pre-diabetic and your grandfather was diabetic, you metabolically probably do better with it. That's what I found.
Yeah, exactly. Right.
And what do you eat when you're eating? What do you eat when you're eating, though? You can't just have McDonald's and Coca-Cola, right?
When I'm eating, look, it's all more aspirational, but I'm trying to cut on carbohydrates. I'm trying to eat more fish than beef. I'm kind of successful. It's very different than 10 years ago, let's say. Olive oil. But really, I think the intermittent fasting already cuts lots of the stuff that I shouldn't eat, and I'm not hungry in return. It's not that I eat more because of that. I don't believe that, and my weight has been good. The third thing is sleep, and so dark room for 8 hours. I don't sleep for 8 hours, but I try. It's actually by my Fitbit. It's interesting. Every week I sleep exactly 6 hours and 40 minutes on average. Okay. And social connectivity, that is important. It's not my problem. I've never met a stranger in my life, so I have this deficiency. but yeah, those are the things. Now, on top of that, let me say that I take metformin. Everybody knows that I take metformin, but I do other things. And the way I do other things, I have a longevity doctor. Okay. And I come with a longevity doctor and I say,
cheating on me?
What should I, what should I try? By the way, I'm on the council of the Healthy Longevity Medicine Society. Are you aware of this society?
No.
Okay. I'd love to connect you there, because we need you, because this is going to be right. I mean, we're going to be the medicine of the future. We're going to improve your health and not get the disease. It's going to be, medical schools will be taught differently.
Totally,
so we need your input there. I'll contact you about that later. But so the longevity, I sit with a longevity doctor, and he says, why don't you try X? And I said, okay, if I try X, what should I test now and after? What will be the decision to go on? And so I tried, I'm not going to tell you what, but I tried other things. Some had effects, some had no effects, but I thought that I want to try, just in order to, it's not an N+1 for anyone, but for me to understand what it is, what it means, what is measurable, and things like that. And I get some information about that. Because of that, I don't care to share. Metformin I can share because we have studies. What I'm doing, I cannot share. But I am trying to
different supplements or different things you try.
Yeah.
you're not just some biohacker doing this on Instagram. You're a scientist who spent your life studying this and has been inspired to do this for a number of different reasons. And one of the things I'd love you to start talking about is your grandfather. You recall him as a very robust, healthy, younger man who was able to do incredible feats of health and fitness. And yet when you knew him, he was older and he had diabetes and was decrepit, and you're like, what the heck? So maybe you can share how maybe that was part of the inspiration for you being interested in this field of longevity science.
Right, but first, I mean, thank you for the flattery. It'll get you nowhere. But look, same with you. You're pioneering your own way, and all of a sudden we find ourselves in the same boat, because aging went from hope to promise, and now we have to realize the promise. So we merge now, and it's really important for me to make sure that we're kind of synchronizing more.
Yeah.
So thank you. And yeah, my grandfather. So
you're from Israel, right? And you're
right.
kind of.
I think the bottom line is when we were kids and we looked at our grandparents, we were like, where did they come from? I mean, what happened to them? Like, you never really see yourself as, that's how I'm going to be, right?
Yeah, yeah.
By the way, I found that this has changed because there's so many younger people who are really interested in aging. But that was for me. And for me, even through medical school, I always said, okay, so cholesterol and diabetes, you can bring me 100 people and I wouldn't know if they have high cholesterol diabetes, but I know who's old and who's young. And that was the phenotype that was much more interesting to understand, and can we do something about it? There's also when I went through my residency, I had a professor, and whenever we presented a patient, we said, so it's a 68-year-old woman, and he said, does she look older or younger than her age? And I thought, what's that? What that has to do with everything? And all of a sudden, you started through this just simple question, understanding that there's a biology for aging. There's chronological age, but there's biology of aging, and it actually has a clinical impact of what you want to do, who you want to give up on, right? And things like that.
Yeah, it's so true. We all intuitively know if you see a 40-year-old smoker has been smoking 2 packs a day and an alcoholic for 30 years, they look pretty rugged. And if you look at someone who's, 65, who works out every day, who eats perfectly, who runs 5 miles a day, they look younger than that 40-year-old. So we know intuitively there's something going on, and that the chronology doesn't actually always match the biology. So your work has really been to understand the root mechanisms of this change in the biology of aging and how we can impact that through lifestyle, through medication, through various compounds that we can study and use, whether it's dietary factors or herbal factors or peptides and all sorts of stuff that are available to us to think about how we influence this process. But what's going on now is this incredible revolution. When I was in medical school, we never even talked about aging. It was like, study diabetes, study heart disease, study dementia, study cancer, the disease of aging. But as you talk about, the biggest risk factor for all of these things is chronological age. The older we get, the higher our risk is for all these conditions. And so now scientists are starting to think about, well, what is at the root cause of these diseases that maybe unifies them? It's almost like the unified theory of aging and disease, like Einstein. I see the picture of Einstein behind your head there. I know you're at the Albert Einstein College of Medicine. And I think, he talked about this kind of unified field theory. What's this unified field theory relates to aging? And how do we think about these key factors that are causing this acceleration of biological aging and the diseases of aging?
So our practice and our leadership has brought us to declare that there are hallmarks of aging. And let me tell you what are hallmarks of aging in my mind, because there's no total agreement. But to be a hallmark of aging, you have to show that something is wrong with aging. And when you correct it in animals or in people, actually, you get an increase in health span and maybe decrease in mortality or increase in lifespan.
Yeah.
This is how you become a hallmark in a conservative way. And the reason we have hallmarks is because something interesting has been observed when you when you correct one hallmark, you influence all or a lot of the others.
Yes.
Okay,
Yeah.
you can improve autophagy, which is our cellular garbage disposal that takes our junk out. You can improve it. It goes down with aging. You can improve it, but you get better metabolism. You get less genetic instability. You get epigenetics changes.
Mitochondrial function improves,
Mitochondrial
right?
function. So
Inflammation goes down, like all of it, right?
So there are practical issues here. First of all, for me, when it comes to what do we call gerotherapeutics, which we used to call anti-aging therapy. We don't use anti-aging because we have geroscience. It's a little, another.
I'm not anti anything. I'm pro health, pro well-being.
But when you use gerotherapeutics, we can take as an example metformin or rapamycin or SGLT2 inhibitor or even GLP-1 agonist, other drugs.
Ozempic, in other words, and other similar drugs. Yeah.
If you go and look at what happens to those hallmarks of aging, okay, they all change. Okay, and people said, "Are you crazy? What, like God created 12 different aspects of this?" And the real point is that those drugs are doing something to repair, to stop aging. So they take basically an old cell and make it younger, or an old organ and make it younger, or a whole body and make it younger. And when it does it, there are lots of things that are corrected. And I remember when it came to metformin, we started arguing, this is what it does, or this is what it does. No, we can decide what happens first, but when you correct aging, you get a lot of effects. So this is one practical aspect. The second practical aspect that is really important, because we want to advance the field, biotech. I'm also an executive in the Longevity Biotech Association. There's a lot of biotech investment, and people would come to me. My job is to help them in due diligence, and they come and say, "Hey, which hallmark shall we target?"
Yeah.
By the way, the question
like, what disease
is,
that's the wrong question. That's the wrong question.
Which is your favorite hallmark? I remember this guy from Texas had 5 daughters. I said, "Who's your favorite daughter?" He said, "I'm not answering." I said, I'm not answering. But the point is,
that's great.
You can target one hallmark, okay, and you improve the others. But that also means that the hallmark, you can do the mitochondria, but you actually have influence not on things that are associated with mitochondria, but other aging thing. In other words, the fact that one hallmark affects the other means that some of the indications for drug development are going to be increased.
Yeah.
So I gave you an example why those hallmarks are important. They're not done, by the way.
There was 9, now there's 12, maybe 13.
Yeah. And not only that, please understand, we say hallmark, and you might understand, I'm not talking about you, Mark, but others might understand that this is the mechanism for aging. They're not necessarily the mechanism for aging. We still have a lot of things to do in order to understand what comes first and what's the combination. But those are practical things that we know that we can fix and have an impact. And that's a good start.
Yeah, it's sort of like physics. We know there's, atoms and electrons and neutrons, and then there's like, quarks and, boson's particles and things we haven't really discovered yet. We keep learning. So I agree.
But once we discover atoms, we already had a lot of advance, right?
Yeah, exactly.
Without the neutrons.
So I just want to drill down on what you just said, because it's so important. And it speaks to the problem with the traditional science and traditional medicine, which is reductionist. What is the single pathway? What's the single target? Which drug do we develop for inhibiting or affecting this particular pathway? And what you just said was revolutionary, is that these are all interconnected. It's a network, and it's a network effect. And these are all connected in a web-like fashion that all influence each other and are all often redundant. So if you actually influence AMPK, which is a lot of the work you're doing with metformin, you're also affecting autophagy and DNA repair and NF-kappa B and inflammation and P53, cancer genes. And you're just doing so many different things that are redundant. And if you hit one of the other hallmarks, you're going to do similar things. And there's so many ways to influence these that they're very redundant pathways. So it seems to me that biology, whether you believe in God or not, how we're designed, evolution, the body was designed with so many redundant systems that were all designed to correct and repair and rejuvenate our system. So in a sense, what's so exciting to me about the hallmarks of aging is it's explaining for the first time these kind of fundamental laws of biology where everything is connected. The body has this innate healing system. It has a profound and incredible healing, regenerative repair, renewal system. And that's what we're trying to target and activate. So we don't treat diseases anymore. We treat these fundamental root causes. And I would even go further to say, what are the root causes of the hallmarks of aging? Because people are still, it's a little bit still reductionist. Like, what's causing the hallmarks of aging? What's causing mitochondrial dysfunction? What's causing telomere?
Exactly.
Causing DNA damage, what's causing deregulated nutrient sensing. And I people say, what's your favorite hallmark? I actually have one. I think the meta hallmark, and you can correct me because you're the scientist here, I'm just the doctor, is I think that one of the meta hallmarks is the deregulated nutrient sensing, because it influences all the others in such a profound way, right? And it's, if you regulate that, which is really through food and our way of eating, what we're eating, when we're eating, how we're eating, all those other pathways that relate to the hallmarks of aging can be influenced.
So you just, first of all, by the way, when you edit this podcast, you should take out my stuff because you summarized it so beautifully. Okay. but then at the end, you did what I kind of made sure you wouldn't do. Who's my favorite daughter?
I know.
And I'll tell you.
Well, that's why I just want you to correct me.
The last, and I came from metabolism, so I don't object it. But the last paper that we all have, the last slide that we have went from seven hallmarks to then 9 hallmarks to now 12 hallmarks, and those 12 hallmarks are saying actually there are 3 groups, and one of them are the ones that are more likely to be the initiators, and the others are going to be the responders.
Yes, that's what I'm saying. Yeah.
So like genetic instability and proteostasis might be more important than metabolism. It's their failure that might lead the metabolic failure.
Interesting.
I'm not judging. I'm just saying what it is.
There may be a hierarchy in what you're saying.
There's a hierarchy, and we want to understand the hierarchy, and we want to see if we missed any of the promoting. But I also want to say that exactly that so we are all, every one of us has hallmark or hallmarks. And we all try to do this picture, to take this picture of hallmark and say, but ours is in the middle, just like you did. Metabolism is connected to everything. And the answer is exactly what you gave before. When Ana Maria Cuervo, my dear colleague here at Einstein, the co-director, when she said, I think autophagy is in the middle because that leads to everything, I say, well, why autophagy is decline with aging?
Yes, okay? Exactly.
There's something that leads the autophagy to decline with aging. Tell me what it is.
Yes, okay? It's the cause of the cause of the cause.
mTOR, that's target for rapamycin, increase with aging. We want to decrease it. Why does it increase with aging? We don't know that.
Yeah, it's exactly right. It's like I think we like to be simple in our thinking, but biology is infinitely complex. Physics is actually complicated, but it's knowable. Biology is almost unknowable. I mean, when you think about, there's 37 trillion cells, and I think there's I don't know, 1 billion reactions in there every second or something. It's like 37 billion trillion chemical reactions happening every second in the body. It's mind-boggling, and I think that most.
And you even ignored the microbiome, which more
Yeah, right.
cells, right?
Yeah, I mean, there was 100,000 terabytes of information just in your microbiome, and I was on a panel with Stan Hazen at Cleveland Clinic once talking about the microbiome and health, and I said, Stan, how much of our metabolites and our metabolome are from our microbiome? In other words, how much of the molecules floating around in our blood that regulate our biology come from metabolites produced by the microbiome, which is from their genetic expression? And he's like, probably a third. And I'm like, whoa, like a third of all our stuff in our blood comes from the microbiome. So we're really, I think in the dark ages, in a way, we're just sort of opening the door. I think with AI and machine learning, we're going to be able to ingest so much information and begin to see these patterns and connections and learn more. And I'm very excited about that.
But I really want to do it more positively. Not that what you describe is true, but okay, microbiome. Well, we know that sauerkraut and kimchi change the microbiome and improve the health, no matter what is okay. So yesterday there was really the best biomarker. I'm in a group that is a consortium of biomarkers, and we had a meeting yesterday at the Bach Institute. It was a meeting that was supposed to be 100 people, but 250 people showed up. Lots of people couldn't register. I'm just saying it was a big deal. And people actually started saying, "Oh God, we have all those biomarkers, and what do we do? And we have to have causative biomarkers in order. We have to understand aging first before even we get to biomarker." And I said, "Look, to diagnose diabetes, you need just one measure, and that's hemoglobin A1C. That's all you need. Okay." Do I know everything about diabetes? Not, but it's not that biomarkers are useless unless I know more. Okay,
no, that's right. That's right.
I think there's a way. Obviously, we're moving on, no matter.
I agree, 100%. 100%. It's like, it's true. You don't need to know how something works in order to actually treat it. I mean, if you eat better, we know it creates, thousands and millions of changes in your biology. And if you eat crap, you feel bad. If you eat good food, your body gets healthy. You don't have to know how that works, but it doesn't mean you shouldn't exercise or eat healthy or do the basic things we know. So I completely agree with you. Not like we have to have everything figured out before we do anything. Although sometimes some doctors and scientists are like that. So this moment is kind of an exciting moment. You've been working at this for decades and decades, and it's almost like all these billionaires somehow got the longevity bug and want to not die. So they're pouring billions of dollars into this space, which is good for all of us. And it's actually allowing the research to really accelerate. And, you're one of the ones who've been studying for a long time. And I want to dive into a lot of the work you're doing, particularly around the SuperAgers and the centenarian study. I want to dive into the science around Metformin and what that is, because a lot of people out there are taking this diabetes drug for longevity. And I have some concerns about it. I know you're the expert in it. You're doing a study to show once and for all what we know and what we don't know. And I want to get into that. But can you talk about this centenarian study that you've done that is about these SuperAgers, what you've learned and how you sort of found that many of these people, don't get sick. They just kind of die. Like, there was a really important paper about the compression of morbidity that was published, I think, in New England Journal in 1980, which talked about people who exercised, didn't smoke, and were optimal body weight, lived long lives, and then just kind of died. They had this rectangularization of the survival curve. They just basically fell off the cliff. Whereas people who didn't exercise, weren't their ideal body weight, and smoked had this sort of long, slow decline, meaning their health span was a lot shorter than the lifespan. And this is what you saw with these centenarians, where they sort of were kind of kicking along and dancing at 100 years old. And I just, had a friend of mine, Norman Lear, died today. Yeah. And I was with him his 100th birthday, and he was kicking up a storm. He was making jokes, and it was fantastic. And I was like, wow, this guy's just great. And very sharp. And
right. And I would add Kissinger, who wasn't dancing, but mentally, he was really sharp. Yes. So absolutely. You described exactly. It's not only that they live longer, they live healthier. It's not only that they live healthier, they have a compression of morbidity. Like 30% of our centenarians don't have a disease. They don't take any drug. They just don't wake up in the morning. One day.
Yeah.
It's actually interesting. The CDC We all know what's the CDC after COVID. The CDC is looking at the medical cost in the last 2 years of life of somebody who dies after the age of 100 versus those that die when they're like 70. And it's third the cost.
Yeah.
So
Yeah.
there is longevity dividend by those example of Lear, of Kissinger, people who just live on, have very few medical records, and then they die. Like everybody, how come Lear died? What happened to him? And that's very typical. But I want to say something else, that because it's an economical thing that I think we should always include when we talk about health span and even lifespan, because Andrew Scott, who's a professor of economy in London School of Economy, said, guys, what are you talking about? You're totally underestimating, because you're saying you're looking at medicine as people in the hospital. Okay, I'm looking at medicine on people outside of the hospital. So if they're not in the hospital, what are they doing? They are traveling, they're shopping, they're buying houses for the kids. And the economical value of just a little increase in health span is absolutely amazing. And by the way, if we don't do it, we're going to bankrupt the governments anyhow. So I think this is very important.
I think the data on that was interesting. It was like $37 trillion for every year. And if you did 10 years, it was like $367 trillion added to the economy. And again, based on that compression and morbidity study, if you are doing bad behaviors and lifestyle, you're going to die long, slow, painful, expensive deaths. Whereas if you live long, you're going to die quickly, painlessly, and cheaply.
Exactly.
So you were talking about these SuperAgers in the Centenarian study, and what are the key takeaways that you've learned from this work that you've done for decades? Because you and Thomas Perls are one of the few who've actually done this and looked at these people.
Right. So let me say a few things before highlighting something. I want to say a few things. First of all, there are we have three hypotheses. One is that it was interaction with the environment, okay, which is not true with centenarians. Half of our centenarians are overweight or obese, even as centenarians. 60% of men and 30% of women were smokers. Exercise, even moderate exercise, house cleaning, okay, and biking and walking, less than 50% of the people. Vegetarian, a little over 2% of the people. In other words, as a group, that's not what they've done. And let's not be confused, because you exactly tell people what to do as far as exercise, nutrition, sleep, and social connectivity, right? So, but that's not it. That's the point. So the second question was, okay, hey.
Although it's a good bet, if you take care of yourself, you're going to do better. So
no, I'm saying absolutely. It's important to note it's good for all of us, but they're distinct by the fact that they didn't do it. So they had something special. So what is the something special? So the second hypothesis was, maybe they have. Now that we have access and lots of us are doing genotypes of 23andMe, we have lots of things that are associated with disease. We have SNPs, changes in the DNA that are associated with Alzheimer and with heart disease and with cancers and all that. Maybe, 1 out of 10,000 just have perfect, we call it perfect DNA, okay? You don't find it. And in fact, when it's already more than a decade that we had the whole genome sequences of our first 44 centenarians, okay? No control, nothing, just 44 centenarians. And we went to this database, CleanVar, and we asked, how many of those variants that are pathogenic variant, which means you'll get a disease, okay, if you have that, you'll get a disease, how much do they have? And to our surprise, 44 people had 230 SNPs. In other words, they had 5 or 6 SNPs that should have made them sick.
Yeah.
Including, we have centenarians who have ApoE4 genotype. If you're homozygous for ApoE4 genotype, you're most probably going to be demented at 60 and dead at 80. And they're 100 and they're not demented.
I had one of those. She was a 93-year-old dentist and was still working, and she was ApoE4.
Okay, so that's the point. So the third hypothesis, which we're really supporting by many ways, is that they have actually genes that slows their aging. In fact, they slow their aging to such effect that if you have some of the junk stuff, it
Yeah,
doesn't matter.
doesn't matter.
Okay,
Yeah, yeah. That's amazing. So basically, you found that there were certain genes that they had that were protective genes, and the question is, based on those protective genes and the discovery of those, what are those genes, and what can we do about it? Because just for people as background, they've listened to me, they know your genes are fixed. You can't change the genes that you have, but you can change the expression of those genes, how they're modified by what we call the exposome, everything you're exposed to throughout your lifetime, your diet, your thoughts, your feelings, your microbiome, toxins, your gut microbiome. I said, everything influences your gene expression. So these SNPs, these variations in the genetic code are not mutations. They're just variations, but they highly influence our health and what we do. So what have you found are the most relevant SNPs that actually extend life and that increase health? And what can we do for those of us who may not have them? How can we optimize those variations?
good. So let me give you an example. I would say that there's remember Paul Simon had the 50 ways to leave your lover. There are 50 ways to be centenarians. We're trying to discover all of them, but there are certainly things that are leading. And I will take one example because I think it's very important, and that's that 60% of our centenarians, 60% of our centenarians have something that impairs the actions of growth hormones. Okay, 60% of them.
Yeah, that's like that Villa Cabamba, those little Ecuadorian people who are really short and they have these growth hormone
Right,
deficiency and they live forever.
right. Those are the Laron dwarf, right?
Yeah, the dwarfs. Yeah.
They have a growth hormone receptor deficiency and they don't get diseases. We don't know if they live longer. On the other hand, in my studies, 12% of our centenarians have a deletion of exon 3 in the growth hormone receptor.
Interesting.
The interesting thing in that, though, is they are much taller than average. Although they have this mutation, they're much taller because it's kind of a mutation that when they go through puberty, and there's high growth hormone level, it's hyperactive. But when growth hormone drops, then growth hormone goes down. IGF-1, which is a peripheral growth hormone, is down. Okay, so there's interesting variation. In other words, if somebody is tall and said, "I heard that you don't need growth hormone," I said, "No, you might have mutation that is good. Don't be discouraged." But basically, and even in our centenarians, a few things. Our women centenarians, most of the centenarians are women. The ones with the lower half of growth hormone IGF-1, it's the growth hormone that we can measure. Half of the women that have the lower IGF-1 live twice as long. They're already centenarians, okay? Centenarians, have 30% chance of dying every year, but those with the lowest live the longest. Also, those with the lowest have better cognitive function. Those with the lowest don't have any difference in physical activity because the question is, does IGF affect muscle? Well, it makes the muscle maybe better, even if not stronger. So this growth hormone mutation is really important. Now, what we did, kind of because we start research in animals, we go to humans, now we have to go back to animals. So we took animals and gave them an antibody against the IGF receptor that was developed for cancer. Didn't work. Cancer is much more complicated than aging, in my mind.
Yeah. and insulin is an insulin growth factor 1 is a big driver of cancer. So it's
exactly. So it made sense. But when we take animal and we give them the IGF-1 antibodies, they live longer and much healthier. So so this is an important system. Now let me explain it in a way that people understand. When we go, evolution is about having children, right? So growth hormone, our body is stronger, we have more muscle, we're able to get, better partner. I don't know. It all works well. Okay.
Yeah. Yeah.
Okay. Now we get to the age of 50, which, by the way, life expectancy through of most of 100,000 years of evolution was between 20 and 30. Okay. So, we didn't get to enjoy 50 so much. But when we get to enjoy 50, then we started to go into aging, and now it really makes no sense for us to spend our energy in growth when we're actually starting to break down. Okay, so I think that there is a hypothesis in aging that's called the antagonistic pleiotraphy. The things that are good for you when you're young are against you when you're old, and that's a perfect example. And we actually proved it by looking at this very good database from the UK, the UK Biobank, and we showed that everybody young, when they have high IGF-1 level, they have less diseases, less mortality, and after the age of 50, it totally switches. Everybody with high IGF gets into a lot of trouble.
Yeah. Yeah.
So I'm pretty sure to tell you that this is important, and I'm pretty sure to tell you that means that for elderly people to give them growth hormone is not a good idea. Okay.
Yeah. I was going to ask you about that because there were some studies. There was one in New England Journal published a number of years ago showing how it improved so many biomarkers and improved muscle mass and health in many ways. And in the whole anti-aging field, up until recently, was really pushing growth hormone. And I was always concerned about it because of its increased risk of cancer and diabetes. And so I'd love your perspective on that, because it sounds like, wow, growth hormone is a good thing in some ways because it increases your capacity for exercise and fitness and well-being and sexual function, everything. But there's a dark side to it.
Right. And by the way, we'll get to metformin, but remember that because it's the same story. I don't think metformin is good when you're less than 50, unless you have diabetic, because they're trade-offs. You have to realize that now we're talking about the biology of aging that is different than the biology of young. And so we cannot assume that everything that was good for young people is good for old people. So we can develop it.
Yeah. So we often look at IGF-1 levels, and there's a lot of people out there in the sort of anti-aging field that are looking at that and go, oh, your IGF level's 1. Well, let's get that up. And I think, to me, it's a big concern because one of my favorite hallmark is the deregulated nutrient sensing. And the first part of that is deregulated insulin signaling. And I think insulin and we're going to get to this with metformin, but as people know my work, I talk so much about insulin resistance as the biggest driver of so much of the phenomena of aging: heart disease, cancer, diabetes, dementia, muscle wasting, and just aging itself. And it seems to be one of the primary drivers, and it seems to be why we're seeing an increase in chronic disease, because our diet is really inducing excess insulin signaling, and it's why we see increased rates of cancers in people with insulin resistance. And it's a big factor with obesity. If you're obese, you're more likely to get breast cancer, prostate cancer, colon cancer, and many other cancers. So it's a really interesting, complicated story. But I think it's like, what is the right way to sort of approach this? If you want to, should we be trying to reduce growth hormone as we get older? Or is this something that we should be targeting? And because you're saying these centenarians have lower IGF-1 and lower growth hormone, that seems like an interesting avenue for potential
right. So by the way, metformin lowers IGF-1. Okay. So for example, metformin does it. Not every drug is doing, but I gave the example. There's also already an FDA approved. No, it's not FDA approved, but there's a IGF receptor antibody in humans that. So we have that. It's safe. It was used in trial, and it's kind of available to think about therapy for aging. So one of the thoughts that we had, even in our study, it seems that the major benefactor for low IGF is women who had cancer in the past, or tumor, any kind of tumor in the past. When they have low IGF-1 level, they kind of live forever. So the question is, should we women after breast cancer, which by the way, they age. Okay, another reason to have gerotherapeutic is to treat cancer survivors. We give them chemotherapy and radiation. We accelerate aging, and then they're older. So For example, should they be receiving IGF antibody? I talked with the companies that are doing that as an ideal, but unless aging will kind of be more an FDA approved indication, I think the pharmaceuticals are very reluctant to start doing that. And another thing that lowers IGF, just that I know, that those fasting regimens are also lowering IGF, some of them.
Well, because you're lowering insulin signaling, right? So, but other things, exercise and keeping metabolically healthy and actually reducing sugar and starch in your diet also, will that reduce IGF-1 as well?
I don't know if it does much of it. I don't know if it does as much. I don't know. I haven't.
So if you become more insulin sensitive, do you have less IGF-1?
Well, not necessarily. It's their from an insulin signaling they share a hybrid receptor, but from a clinical point of view, the relationship between insulin level and IGF-1 are not really great. So I'm not sure. I haven't seen a study that I can quote, even though it's an interesting question.
Interesting. Now, I want to talk about something else that you found in your SuperAger research, and that has to do with some of the other common traits that they have. You mentioned the really low levels of IGF-1, but they also had high levels of HDL, or high density lipoprotein cholesterol, which is people refer to as the good cholesterol, but there's no good and bad cholesterol. There's just different functions of the cholesterol. And I remember years ago, I had this old guy who was like a pathologist from Quest Lab who gave a talk, and he said, I realized we have all this data on people and we really don't know what the phenotype is because we just get their lab data. We don't know actually what happened to them. So he wanted to research what affected longevity, and he decided to look at HDL, and he basically went and found all these people who had a high HDL in the Quest database. And then he tracked all their death certificates, and he found this incredible correlation between high HDL and longevity. Now, which is fascinating because, when we looked at certain drugs that are the CETP inhibitors and others that actually seem to raise HDL, they actually have the opposite effect, right? So naturally having it may be good, pharmaceutically elevating it may be bad. What's your thought on this whole thing? And there's new versions of these drugs that are about to come out as well that we don't know. So I find it very fascinating. And I think, the things we do know is that sugar and starch lower your HDL and that exercise increases it. So, and good fats, and also like coconut oil and saturated fats will increase your HDL. So we know some ways to modify it, but I'd love to kind of hear your perspective on this.
Right. So we discovered very common genotype. But by the way, what I'm describing are functional genotypes that we know. There are lots of SNPs that, they're everywhere and we don't know if they're functioning. I'm talking about very functional genotypes. And we found functional genotypes on the CETP. That's one of the genes that control those cholesterol, HDL, lower triglycerides, and another thing in a gene called ApoC3. And the pharmaceuticals was very interested in our research, and actually Merck has developed. Pfizer failed for another, Pfizer didn't develop a right drug. Okay, it was a drug problem. Okay, it caused hypertension. It was something else. Merck developed a CETP inhibitor, and a company that, what's their name? They used to be ISIS, but then they had to change the name. They're Ionis now. Ionis developed an antagonist to ApoC3. Both are changing, and they, by the way, they didn't develop it for longevity. They developed it for lipids.
And the ApoC3 will have your triglycerides will go up if you have ApoC3, right?
No, right, but right. Our genes are inhibiting the CETP and the ApoC3. They have to be lower, and so those drugs that are inhibiting those are coming out to the market. With Merck, one of the interesting thing, our centenarians who had this mutation in CETP, they're distinct from other centenarians because they had an incredible cognitive function. Okay, this was better even than heart disease or anything else.
If they had lower ApoC3 functioning.
Right. And so I asked Merck on the CETP, I asked Merck when they did their study to look at cognitive function. And they didn't have any association, but I think that they had the wrong population with the wrong test. If you do cognitive function on 50, 60 years old, you're not going to get much change in cognitive function. You need some, for the test we have, you need some other population. So I'm still thinking that this CTP will come in, people will start thinking about it, and I'm thinking when this CTP will come in, I'm thinking I'm going to take it because the cognitive function signal was pretty amazing.
It's interesting. I actually have done my genes, and I have the good version of the CETP and the bad version of the ApoC3, and it tracks. My HDL is higher, and my triglycerides are also higher than I would expect given my diet and lifestyle. I mean, they're not stupidly high, but I'm like, why is my triglycerides 100 given what I eat? And I can get it lower, but it's just so fascinating to see how we're going to be able to sort of track our genotypes and then see what works for us and create this personalized approach to health and longevity, which is where it's all going really fast.
But in a total surprise, I have one of by 23andMe. I have one of the IGF receptor genotype that I published.
Oh, okay. Yeah, so you're going to be doing this a long time then, huh? Here, we're going to keep going. We'll do another podcast when you're 100.
Let's do a deal like that.
And the other thing that you found was something else that was in the SuperAgers called high levels of MDIs. Can you explain what are MDIs, what that is, why it matters, and what you found?
So this is kind of a surprise. And I have to say, I have a guy, Hassi Cohen, who's the dean of gerontology at USC. We went to medical school together. By the end of medical school, we published together like 8 papers, and we're collaborating ever since. Though he's a pediatrician, but he's the head of gerontology now because I influenced his life so much. But we had a grant together. And he was looking at partners for not the IGF, but there's IGF binding proteins. It's a complicated
IGF-BP3, right?
And he kind of fished a peptide that eventually was known as humanin. Humanin is coming from the genome of mitochondria, right? So we have at some point of evolution, early evolution, our cells were kind of miserable and pathetic, and we needed some energy, and we got this bacteria, and mitochondria is really a sign of bacteria, and we adapted to be symbiotic, and that's the source of energy. But those mitochondria, and we often forget, have their own genome.
Own DNA, right.
Their own
DNA. It comes from your mother.
It comes from your mother, right? It has your own DNA, and also it has mutations on your DNA, but it's not only that. This DNA produces peptides that eventually you can measure in your blood, and when you give those peptides, they do stuff. So humanin is one. So we started actually a company to try to develop at least good, part of the things when you develop, those are peptides. When you develop the peptides, you actually have to have them act longer, and you have to find things that are more with higher efficacy and stuff like that. So we developed a bunch of those peptides. And on the way, we found really interesting things. I'll give just one example. One of the peptides that we developed, we looked at genome of Asian, Korean, Chinese, Japanese, and they had 8% of them had mutation in this peptide. And when Hassi measured those peptide activity in the lab, they weren't so active.
Oh.
Now, those people, those 8% had 30% increase in risk of having diabetes. Okay, so by the way, genetics is so important now because 2/3 of the drugs that FDA approved last year were based on genetic studies. It's no longer that you work on mice or nematode and say, let's develop a drug. It doesn't work anymore.
Yeah.
Regeneron, all the pharmaceuticals, they want to see population that have overactivity, underactivity of this peptide and have a disease. And then you can develop the drug fast and more effectively. So it's very important for us to get signal from population that also showed you that, by the way, it's called MOTSI, this gene. So it's very important to show that there's a relationship between genetic study and actually diseases in humans. So you have more confidence that there's a causality here.
Yeah, so interesting. A lot of people are using peptides now, like MOTS-C, Humanin, and you mentioned earlier when we were chatting before the podcast that MOTS-C can be helpful, but then you develop antibodies to it, which may have other adverse effects we haven't understood. So a lot of people are playing with peptides. Do you think it's safe? Do you think it's risky?
No, look, I understand frustration of people, okay, and I think that that the frustration leads to shortcut. And when you say maximize your exercise or diet and stuff, you're not really causing harm usually. But when you're taking you're taking peptides that you don't still understand everything about them, and you manufacture in a way that's probably doesn't make sense. There are companies that are happy to give you these peptides, but actually, for example, in the MOTS-C, it was hard to find actually a solution that will hold this MOTS-C without getting them to cling together, and we couldn't get them any blood level. So there's so many things with those peptides that you cannot assume I'll order a peptide and inject and it will be thing. I think it doesn't make sense from this sense, and then it can be dangerous because we don't know how much, and generally drugs, there's too much for drugs and too little for drugs. So I think it's a wishful thinking, and I wish, look, we both of us, right? I mean, we went to medical school and the first thing they teach us is do no harm. So we're conservative, right? We belong to the half that will actually do something for people, but most doctors let's do no harm. So let's not. And then, by the way, the next day they teach us rightly that there's no always and never in medicine. So what about using a drug that saves 100 people and kills 3? How do you weigh that?
Yeah.
So
exactly.
I think it's important for us to stay conservative. It's important for us to say we need clinical studies, we need a real development, and kind of stick to it, because otherwise I think the chances of doing harm are really much
more. Yeah, and it's so personalized too. I mean, I just remember a story of a young man, I think his name was Fagenbottom, who basically was a medical student and developed this very rare cancer. I forget the name of it. And there was no treatment for it. You probably know this guy. And he's amazing. And he was this, super fit football player. And then he just became emaciated, went through multiple rounds of chemo. They told him he was gone. He was just, ready to get his affairs in order. And he decided, well, I'm a medical student. I'm going to start to research this. And he looked at the proteins expressed in his blood and used, very basic scientific techniques and found this huge spike in mTOR. And he was like, mTOR is good because it helps you build muscle, but overexpression can cause overgrowth, not just of muscle, but of cancer cells and other things. And so he said, well, I'm just going to try rapamycin because that's one of the drugs that actually inhibits mTOR. And it completely cured his cancer. And he's amazing, healthy, great guy now. And he continues to take this drug. So it speaks to some of these pathways that are at the root cause of cancer. He's not taking chemo. He wouldn't do radiation. He didn't do surgery, but he used sort of molecular medicine to understand what his particular tumor was doing and what he could do to modify it. So I think
incredible story.
It's an incredible story.
I forget the name of this guy, but incredible story.
I think it's Jason Fagenbottom. He wrote a book. It's great. So I think that's so important. So now I want to sort of shift to talk about your work around metformin, because I think it's really interesting. And I think, as we talked at the beginning, there is no silver bullet or there's no magic trick here that is going to fix everything. And I think people are always looking for what's the pill I can take? What's the supplement I can take? What's the peptide I can take? It's going to fix it all. And I don't have to worry about what I'm doing and how I'm living and whether I'm drinking or eating bad or exercising. And that's really not the purpose of this. But, you're doing something that's really important, which is you're doing a very rigorous clinical trial on a compound that seems to have some evidence that it may improve many of the biological factors and the hallmarks of aging. And that's called metformin, which is a drug developed in 1957 to treat diabetes. It's been around for a long time, and it's one of the first line therapies for it. And you're doing this not just to study metformin, I think, but you're doing it to actually show that we can treat aging itself. And if this is successful, which I hope it is, I think it will shift the whole field of the NIH and the focus of longevity research, which is what I hope it does. But I kind of want to just sort of set the stage for a minute and talk about why we think this is so. And I think there was a paper in 2014 with 78,000 diabetics who were studying this group on metformin versus non-diabetic controls. And it seemed that there was about a 15% lower survival time in people who were not taking the metformin. And there were some challenges with that study. There was another study published in 2022 that was another observational study, but completely contradicted that study, which was the Danish Registry Case Control Study, where the metformin monotherapy group increased mortality, like I think by 50-something%,
compared to non-diabetic.
Yeah, compared to non-diabetic. So one study showed that if you were a non-diabetic, your risk of death was greater if you weren't on metformin, and the other study showed the opposite in quite a significant way. So I think that's kind of like it needs to be answered, and this is why you're doing this clinical trial.
Well, no. Look, I think that was a distraction. I think it was a distraction. But let me say first, I want to correct something.
Oh, please.
Between 1920s and 1950s, okay?
Yeah.
Metformin is an extract of the French lilac. So it's kind of nutraceutical, but it's not. It's modulated. You need a prescription. Actually, you don't need a prescription. You can go in Amazon and get it for a lot of money. It's
Really?
not a lot of money, but it's 10 times more than it costs. And at that time, why did people use it? Because people noticed that people who takes this French lilac extract it was treating arthritis, it was preventing flu, it was even preventing malaria. It had lots of benefits. And at that period, people noticed that people who had diabetes and took this drug, it lowered their glucose. So it was kind of hijacked for diabetes. But actually, it had all those other properties that were ignored. Now, since it's used for 80 years for diabetes, there are lots of other studies that showed, and by the way, studies have showed that it prevents mortality in variety of studies. Okay, I'll get to those studies. So in clinical studies, those that you mentioned are not clinical studies, there are association studies.
They're just population studies where they look for correlation, right. But it doesn't prove cause and effect. And they showed the opposite
studies,
effect.
There was the UKPDS, there's lots of evidence that metformin decreased mortality, but even or supporting of that, people on metformin have less, first of all, there's the DPP, they had less diabetes. Non-diabetic patients get less diabetes. People with diabetes have less cardiovascular disease, they have less cancer, they have less cognitive decline, they have less Alzheimer. So there, and a big effect in clinical studies. So for me, it's not about proving metformin. It's not that at all. The reason I'm doing TAME is for the other reason that you said. We have to show to the FDA that we target aging, the biology of aging, and we prevent age-related diseases.
Yeah, the study's called TAME, Targeting Aging with Metformin. Right?
Yeah. And really the idea is not to repeat the studies that were done. And by the way, because metformin is FDA approved, so it's safe, because there are so many other studies, a lot of doctors are repurposing metformin based on data that they have. Okay, it's
I know a lot of people who are taking metformin for longevity, and
right, exactly. Metformin is repurposed for PCOS. Metformin is repurposed for pre-diabetes, which all of them are not FDA indication. We repurpose drugs all the time. So the idea is to show the FDA in a clinical studies that a cluster of diseases that include cardiovascular disease, cancer, and cognitive will be delayed or prevented in a certain period. It's a hard concept in the sense that we are saying we're targeting aging, so we're agnostic to what disease you're going to get. If your mother was diabetic and you are obese, you're going to get diabetes, right? But I don't know. We're going to change your aging, and for every disease that you're going to get, you're going to get a point over time. And we're going to show that metformin will delay that based on existing study. So it's all about how we prove to the FDA that aging is, that we can prevent.
Treatable. It's treatable.
Right. We can prevent diseases. And they, by the way, they agreed. They don't buy that we can do something with aging, but they said, if you have a trial that shows that you can prevent all those old related diseases, you should bring it on. And we don't care. We kind of don't care to call it aging a disease now, because we know what to do. Okay. So, but this is really the main point. But it has consequences. First of all, this is we were a really great team that planned how to do this study, and this is a template for the industry. You don't need many patients. You know, if you were developing a diabetic drug now, you needed 12,000 people in a cardiovascular study also to prove safety. We're talking about 3,000 people between the age of 65 and 80, because we're not looking at diabetes, we're looking at every disease basically. So you're going to get one. After 65, you're going to get one, no matter what, right? So we need only 3,000 people. The second thing is, pharmaceuticals are kind of waiting for that in order to jump in and get into buy those biotechs in aging and develop drugs, because they need an FDA route. They need a business plan, and business plan developed with the FDA. And also for us, healthcare providers don't have to approve any drug that's not FDA approved. Now, it's easy with metformin because it's the cheapest drug in the US formulary, but for industry, no doubt that some of the first drugs that will come will be as expensive as GLP-1 now, right? As any drug for a few years. But for the public, having metformin is going to be really an advantage immediately.
Yeah, I mean, I think it's important. I want to talk about the mechanism of action, because as we sort of talked about earlier in the podcast about how all the hallmarks are connected and how there's so many redundant pathways, and how affecting one of these pathways can affect other pathways. So, from my understanding, the main action that we understand of metformin is to activate one of these, I call them longevity switches, these deregulated nutrient sensing pathways. And one of them is AMPK, which detects low nutrient energy levels in the body. And when you activate that, it creates a cascade that inhibits inflammation, that activates sirtuins, which improve DNA repair and improve mitochondrial function, and inhibits mTOR, and it maybe has other mechanisms of action in the microbiome, which may be interesting to me. I don't know how that exactly connects into all this. Maybe the mechanism is that it optimizes your microbiome. And, so I'd love you to sort of talk about some of these. And I also want to sort of dive into one of the what I think are potentially a risky aspect of metformin. The things I just mentioned are all positive, that all beneficially impact the hallmarks of aging, but it's the inhibition of something called mitochondrial complex 1. And this is one of the most important steps in producing energy in your cells and to build muscle. In some of the studies I've seen, you actually giving metformin will limit or prevent any increase in muscle mass and a muscle density gain when you take metformin and you exercise. So if you do weight training, it kind of blunts the effect of weight training, which kind of is worrisome to me as I think about frailty and aging and building and keeping muscle and preventing sarcopenia. So maybe you could talk about some of these mechanisms, how they all interconnect, how you think they influence all these phenomena of aging, and then maybe chat a little bit about this concern that I have and whether I'm right or wrong.
Yeah. Um, so, I think it's best maybe that I'll give an example and follow it because I got involved in that at a certain time. So, um, when you take a group of 75 years old, and this is a study by Charlotte Peterson in Kentucky, and she had a grant because she said, if I exercise and give metformin, I'm going to get even better response. And so she took those 75 years old, half of them exercised, the other half also exercised, but they were also on metformin. And by the way, when they exercise, whether you're on metformin or not, you build up more muscle, but you build significantly less muscle when you're on metformin.
This is the master's trial you're talking about?
Yes, the master's trial. Okay. So basically the paper was like, metformin inhibits muscle size. So that's where scientists have to come in, because I'm reading the paper with interest, including all the supplements. And supplement 2 shows that they also did an assessment of muscle function. 4 different things. And those 4 different things were not different between the people on metformin and without metformin. So if the people without metformin had bigger muscle, what does it mean? Does it mean that really for every gram of muscle, metformin is actually doing better, right? If we think in the Einstein way, that's really what it means.
Wait,
so
I lost you there. Can you kind of explain that again? I didn't make the connection.
If you on metformin have smaller muscle, but you have the same power, then every gram of muscle is better.
I see what you're saying. So you don't lose muscle function, but you lose muscle mass.
Okay. So then I said to Charlotte, can I look at the muscle? And I did several things with the muscle, including the transcripts. And the transcript shows, I think, what we kind of knew.
The transcript is basically all the things that are transcribed in the proteins.
Right. I'm sorry. I shouldn't assume, but
I'm a doctor. I get it, but I don't think anybody was on transcript.
No, I know.
It's a written transcript of a paper. No, it actually has to do with the DNA replication and transcription of proteins. And
So this is where the paradox is. In order to build muscle, you need mTOR. Okay. So if you need mTOR, you already know that if you use rapamycin, which is a strong mTOR inhibitor, or metformin, which is also a major inhibitor, which is really important for the aging of maybe the rest of your body, you're going to pay with the muscle. So we showed on one hand that the transcript of mTOR related genes are really decreased. On the other hand, we found that other genes that are important for aging, such as for autophagy and for inflammation of the others, are getting better. So basically you have a muscle that is smaller but is better in quality. That's when you're old.
Interesting.
Look, I think I think the reason that's a controversy, and so by the way,
just mitochondrial health is such an important feature of healthy aging.
But
it's one of the biomarkers, hallmarks of aging.
Look, targeting so metformin does what you kind of described. Let's call it the metabolic, the AMP kinase pathway. By the way, metformin works also in animals that don't have AMP kinase. Okay, it's kind of weird. And metformin also ends when you don't have mitochondria in a row zero cell. So it's really much more complex because it's doing some things. But what happens on the mitochondria? Yes, you increase the transport of electrons, and by that you also decrease oxidative stress. And in this pathway, you also decrease inflammation and other parts. So actually it's important, but it's also important for another reason. Because if you look at VO2 max, which is a really good tool to assess your health, okay, if you have mitochondria,
Can we just stop there? I want to tell people what that is. That VO2 max is basically a measure of your fitness, and the higher it is, the longer you live. And it's really basically a measure of the function of your mitochondria and how quickly they can consume oxygen, how much energy they can burn in a minute. So Lance Armstrong has a very high VO2 max, whereas a diabetic, might have a very low one. And it's really a reflection of your mitochondrial health and your fitness, and it's directly tracked to longevity. So
right.
Yeah.
And this marker for metformin is not good, because you have to understand we're not we're not on a VO2 max in our life. It's like you come from metabolism. Remember, we used to talk about insulin sensitivity and insulin responsiveness. Insulin responsiveness was take the insulin level to 1,000 micrograms per ml, not relevant to our life, and see how much glucose you can actually push them to the muscle, which is not as relevant as let's get your insulin level to 100 micrograms, which is like after meal, and see what's your sensitivity in, and you can have the increased response. I think the same thing people are not thinking about. The VO2 max, I think metformin is doing lots of things. It doesn't prevent you to exercise. If you want to check if your VO2 max, I think you're not going to be at VO2 max if you have a good metformin, but I don't think this is really a measurement of health when you're on this drug, just like as you're not going not to take rapamycin ever because they inhibit muscle. I think the more important point here is that when you're young, when you're old, those things help repair. Rapamycin and metformin, they touch a lot of the hallmarks, they have repair. When you're young, they're going to lower your IGF-1, they're going to lower your testosterone in several instances. All those things that we don't know, or your exercise capacity, or your ability to do push-ups and weight. So I think it's very different how we think of those drugs when it comes to old body and to young body. And yes, they're trade-offs. Okay, there'll be trade-offs. But
I've heard of some people saying I'm not taking metformin on the days I do my strength training. Does that make sense?
I know, or the same hour or hours. Look, this is my spiel. Okay, the major side effect of metformin is that you might live longer. And you might not be able to afford it, okay, or something, okay. But those drugs have good, because if you're a sport medicine, if you're Peter Attia, then all you care is the muscle, okay. But metformin, just like exercise is not about the muscle. Exercise improves cognitive function and immune function and other things. So I'm not sure metformin is good for bodybuilders, but it's also good for other things outside of the muscle.
Yeah. That's fascinating. That's fascinating. So it's such a nuanced story, and you're right. There are so many benefits of metformin that are, we call pleiotropic. When a drug, typically in medicine, we think of a single drug with a single target, and anything we don't like is called a side effect. It's not really a side effect. They're just effects of the drugs we may not like, or that we may like in this case. So metformin has all these side effects that are beyond lowering blood sugar that actually may extend our life, which is so exciting. So I'm very, very excited for the TAME trial. I think.
Sorry, I just wanted to, before you move from metformin,
I'm going to keep going. I have more to say about it, but you go ahead.
I just want to go back to, you started by those two studies, okay? That they were not good studies. And I have to say, I populated the first one. I populated because it was cool. I knew that it's not a good study, but I thought, it's kind of study that you show that people with diabetes on metformin might live even longer than people who don't have diabetes. The Danish study was a different study.
A twin study,
but one of there are few problems that we should know. First of all, the study didn't show the mortality of people on metformin, diabetic people on metformin versus not on metformin, which is for me, because yes, when you're diabetic, you're running into more problems. So just show first, you have the data, you have the registry, and I know that they showed that there's less mortality, that they just didn't want to put it in this study. Okay, they just but the reason there's difference in my mind. And by the way, the problem with twins. The twins, a lot of time, are born low for gestational age, right? In fact, one twin is usually born smaller than the other twin. And this is kind of the Barker hypothesis. Those twins, those small for gestational age, can run into aging rather quickly. They get diabetes, they get hypertension before others. So the twin study, if you don't adjust for birth weight, I'm very skeptical about it. But I think the major reason for the difference, I mean, there are so many differences, but I think the one that explains a lot, one is in the UK, where at that time obesity was 20% in the population. Of course, all the diabetic were obese, but also 20% of the other population were obese. When in Denmark, the rate of obesity was 10%. So basically, it means that the Danish diabetics are obese when the rest of the population is not obese. So you took one of the risk factor that would adjust through insulin resistance and other, right? To those.
So it's the devil's in the details, right? It's like, and the problem is, most people just get the headlines in the newspaper, and often the headlines get it wrong. And I read one study in actually the New England Journal, but abstracts don't represent what's in the body of the paper, like over half the time anyway. So it's like, it's hard for the average person to kind of make sense of it all.
Well, an example that's relevant to metformin, and actually it's a very important example. Look, there are 9 studies from in the COVID times around the world that people on metformin had half the hospitalization and half the deaths.
Yeah.
And then there's a New England Journal clinical study where they gave metformin to people within 3 days of getting COVID. And it prevented 40% hospitalization, 40% death. And then there's a follow-up study in the Lancet that it prevent long COVID by 50%.
Well, it's interesting mechanistically because, one of the drivers of that is uncontrolled inflammation. And one of the mechanisms of action is it inhibits this transcription factor, this thing that causes your genes to be expressed, called NF-kappa B, that influences cytokine production, which are the cytokine storm inflammatory signaling molecules. So basically, if you take metformin, you're inhibiting the driver that causes your genes to produce all these cytokines. So that maybe that's the mechanism. I don't know.
Well, more than that, because it has effects on the immune cells themselves, on inflammation, but on the immune cells. But it also affects the whole body to sustain a terrible, a heart disease when you're old, right? You need a body for that. But I think it makes the point that we talked about metformin and muscle and stuff like that. But look at metformin and COVID. If you take it within the first 3 days, you can do much better.
Interesting. Yeah. Okay. Well, I want to talk about a few more things about metformin. I'm not done yet. And you're the guy. So while I got you, I'm going to ask you, tell us about the microbiome effects, because I've talked to some folks about this, and I think there's some research in Israel around this and how maybe the impact on our gut and our gut microbiome may be playing a big role in some of these benefits. Can you share what we know about that and what it does to our microbiome?
Yeah, I totally agree. I think it's a potential important link. But by the way, I'm kind of the fence with microbiome and the aging aspects. Okay,
it's one of the hallmarks of aging now, right?
It's now
changes in the microbiome.
It just made it to a hallmark of aging, and I think it's maybe not strictly. It's not strictly my definition, but certainly, I don't think there's enough models that show that you can increase survival with any manipulation of that. But there's certainly a study that showed that that people on metformin had a change in their microbiome that had a benefit effect. There's more to the study than that. It's very compelling. It's not only metformin, acarbose, which is another drug that in human prevents mortality not related to diabetes, also has effect on the microbiome. So I'm pretty sure that microbiome are important. And but that's kind of the thing. We're saying, is the microbiome changed by metformin in the gut, or is it changed by metformin in the body? Because metformin changes all the hallmarks of aging. Yeah, so it changes microbiome. So is microbiome a bystander? Is it important? It's kind of hard in this way to depict, but I want to say that there are drugs that change the microbiome, and I'm convinced that microbiome has a role. I don't totally get it, but it has
Have
a
they
role.
mapped out the particular bacteria or bugs that actually are increased or improved? Like Akkermansia, for example, is improves metabolic health. Yeah.
They had the whole genome. It's an old paper already, and there's more sophistication and maybe more studies of it's really not about the type of bacteria, but their metabolic profile. What's the metabolite that are actually absorbed into the gut, things like that. I think there's more sophistication, but I would take it as a fact that metformin changes microbiome.
Okay, now I want to play devil's advocate for a minute here and challenge a little bit the theory of metformin, because there was a study that was done, a very famous study called the Diabetes Prevention Trial. And it was, decades ago, but it showed the impact of lifestyle compared to metformin, compared to nothing for preventing the progression from prediabetes to type 2 diabetes. It was about 1,000 prediabetics. And they found that if you took metformin, it reduced the progression to diabetes by about 31%. If you did a lifestyle intervention, which, by the way, at the time, and I knew people were in the trial, was a low-fat intervention, which is not the diet you want to put a diabetic on, but they had other things like exercise and social support and so forth. They reduced the progression by 58%. So in this case, I'm wondering, is it possible to achieve all the benefits that we get from metformin and even more benefits with more aggressive lifestyle intervention? And do we actually need metformin?
You're assuming that they're doing the same benefits, right? And not different benefits. But look, first of all,
and I understand there's all these other kinds of influences of metformin besides blood sugar and diabetes.
Right. And let's agree that that exercise, all the lifestyle, exercise, diet, and stuff have a major impact and could be maximized at every time. Okay, let's agree on that. This is my question. Look, I'm a diabetologist. I'm actually on Thursdays, if I'm in town, I'm seeing patients. Okay, I'm not a geriatrician. I'm a diabetologist, and so 30 years in my clinic. And it's a fellow clinic. So I see quite a lot of patients. So first we tell them, okay, diet and exercise. We send them to diet stuff and we tell them how to exercise. How many people are doing that? 3% in the Bronx. Okay. I'm sure you have more success.
Well, sure.
Okay?
I mean, it's not whether it works or not. It's whether you do it or not. Well, you have to take metformin in order for it to work. If you don't take it, it's not going to work, right?
Right. Exactly. So I think, diet and exercise, and I'm thinking, who needs metformin? Who needs metformin urgently? It's not us, okay? Because we know how to deal with our health. It's poor people, okay? Poor people are obese. Poor people don't have access to exercise. You don't give them money to buy trade-off or to get into gym because they don't have gyms. For nutrition, you want them to have more vegetables. Well, get them more vegetables. You want them to have more fish. They don't like fish. So actually with Andrew Scott, we did kind of this, how many dollars metformin versus what you need to do to change lifestyle for a population? It's 1 to 100,000. Okay.
Maybe. I have a different theory, but yeah, I hear you. Yeah. I hear you.
Yeah. I think we need geroprotectors, and geroprotectors will get better and they'll get in combination and they will enable us to go beyond the lifestyle. Okay. I've no doubt about that. And it's a consideration, but I wouldn't look, DPP was here in this area too. And I more use it to show that if you say, does metformin work on non-diabetic? Well, the DPP was non-diabetic. They were at increased risk, but they were non-diabetic. And it's a 30% effect, and a 30% effect of every drug is pretty incredible.
Yeah.
And the lifestyle intervention of the DPP was amazingly, it was very, very expensive. Okay, they did have to go to the gym to train them, to give them food, things like that. So,
well, we actually created a program. I did a program with at Cleveland Clinic at our center, which is a lifestyle change program. And we actually measured the cost of the program compared to conventional care, the outcome improvements. And we basically saw it was 3 times as effective and more cost effective by doing kind of shared medical appointments, essentially. So there's ways of delivering care and doing things that I think are not what we normally do that actually work. So it's not that we just haven't figured out how to get people to do the thing, but that's a whole nother conversation. The other thing I sort of, wanted to talk about is for someone like, me, or asking for a friend, my insulin level's 2, my lipids are perfect, my body fat's 10%, I exercise all the time, I eat perfect, have a low glycemic diet. Am I going to get added benefit from taking metformin, or have I already kind of tuned things up? Is there something that I should be thinking about? Because I want to live for a long time, and I'm like sort of on the fence about it. And you don't have to answer, but I'm just like
look,
asking for a friend.
I'm kind of making point that I'm a data person. No, I don't have a data, and I wouldn't really recommend you unless you get into some trouble. Like if you would tell me, I'm worried about my cognitive function in spite of everything, I would say, maybe you should consider rapamycin or metformin or something else that's coming. But no, I wouldn't. Look, it goes back. Your biological age might be less than 50, right?
It's 43, yeah.
So why would you take metformin? That's my point. And it's not age; it's the biological age, right?
Yeah. Interesting, yeah. So I think it's interesting. It's I think we're clear. Someone has metabolic health issues. It's not a bad thing to do. And I prescribe it for those who need it. I think I'm not yet ready to prescribe it widely for healthy people who are looking for a longevity benefit. I want to see what the TAME trial shows. So I'm holding out. So hurry up on that. The other thing I wanted to sort of just bring up is other ways that we can have similar effects. And maybe I'm out of school here, but you mentioned that metformin was from this French lilac, and we know there's a lot of things that actually also influence the same pathway, AMPK, which has all these downstream benefits we talked about. Obviously, exercise, saunas, various phytochemicals, and there are a lot of things that have been found to have similar benefits to metformin, like saffron, berberine, resveratrol, ginseng, reishi, mushrooms, artemisia, black cumin seed, bitter melon, which is like a Chinese food, tangerines, chlorogenic acid from coffee, capsaicin from peppers. So I mean, if we start to include all these phytochemicals, as a way of regulating AMPK, you think that might have similar benefit? And can we start to look at those things?
Okay, so I'll tell you my worry, and I'll give an example. If let's say you take metformin and rapamycin and you increase the dose and you subtract and you stop mTOR.
Yeah.
So, for example, your plasma cells are totally mTOR dependent. Okay. So, what I'm saying, if you add, we are assuming that if you have those longevity nutraceutical or drugs and you'll add them to each other, they'll be additive or synergistic.
Yeah.
And in fact, I'm afraid that a lot of them will be antagonistic. Okay. Or you'll get, and my worry is more our friend Brian Johnson, who takes 115 supplement. And we measured our Grimm age together, and I'm 3 years younger than my age. He's 4 years younger than my age, but I'm not doing 115 supplements. So I think he's paying off. I think the supplements are problem. I always say they're great for the economy. Okay. They're great for the economy. They drive a lot of business, but I would say that we don't know enough, not about the supplements, but how you add them together. And at what point, I said before, every drug, if you take a lot of it, can be of a problem and can be a problem at a specific person. So I would just say, yes, we need clinical studies. We need more clinical studies, even in animals, to show whether it's additive or antagonistic. Exercise and metformin are antagonistic on the muscle, right?
Right.
We have those examples. So I think it's a good question. There are all those things, and my worry is that people just wrote down the list and they're buying everything, and they're
No, don't do
promptly there,
that.
and
Don't do
they'll
that.
say,
Don't
"Why
do
am I sick now?"
that. Don't do that. No, it's the point is that, there's so many natural compounds in our food. And I think, you can't get into trouble if you eat all these things. If you have bitter melon in your diet, and you have, saffron in your food, and you have, coffee in the morning, these are not going to be problematic. It's when you're taking pharmaceutical doses of these things that you're going to get in trouble. I also just sort of want to, I'm going to want to talk to you forever. I know we have to sort of end soon, but what are the top geroprotective molecules and drugs that are under research now? I think you obviously focusing on metformin, but there's NAD, there's rapamycin. What's your take on what are the most promising things out there?
So we published, and now I'm submitting another update paper. We did a paper on repurposing FDA approved drug that showed to increase longevity in mammalians, not in nematodes.
Yeah, not in worms, humans or mammals, right?
Right. We have a scale of 12. 6 belongs to the geroscience, hallmarks of aging, lifestyle and health span of animals, and 6 are human. And the 4 drugs that are, and this will surprise you, metformin comes only second, okay? The first drug is SGLT2 inhibitors. SGLT2 inhibitors is a fascinating story, but in short, is developed to diabetes. Basically, you pierce your sugar, and that's why your sugar will be okay. But for some reason, people notice with whether you're diabetic and then non-diabetic, when you take it, you get less kidney disease, less heart disease, and decrease overall mortality. Checks out everything. You give it to animals, they live longer. Okay? So SGLT2 inhibitor is actually, and I'm kind of considering maybe to switch from metformin to that for a while and see what happens. I think this is, and by the way, I'm taking metformin because I was pre-diabetic and I really benefited from it. But because you're not taking, I didn't want to say, I just wanted, and the second is metformin. The third is etidronate or biphosphonates. Biphosphonates is another example. We don't know
for
where
osteoporosis drugs.
Osteoporosis drugs. I heard about it the first time because there was a paper, women in ICU on biphosphonate, they don't die. And then they started to test animal, they started to test in human studies and in control studies. And there's decreased mortality for people on biphosphonates, which we don't understand the mechanism yet. There's a lot.
And it's not just because they don't break their hip and
no,
die from that.
It could be action, but the bone has your bone marrow. There's immune cells. There's a lot of stuff that happens. And the third that we got is the Ozempic, the GLP-1 inhibitor. Remember, when I went into aging, the only model that we had was caloric restriction. Yeah. You took animals, brothers, half of them ate whatever they want. The other were calorically restricted. They lived 40% longer and much healthier, like our centenarians. So GLP-1 is a calorie mimetic, and I would say that obesity drives aging. Okay, obesity drives aging. So to use GLP-1, and people are using it creatively. If you're obese, they'll give you GLP-1 for a while and then put you metformin to keep on the weight, things like that. But those are the 4 drugs that should be considered for repurposing in that order now, based on evidence.
So the first one is metformin, or what was the first one?
SGLT2 inhibitors.
Okay, but then the Ozempic.
The second is metformin.
Oh, okay. Okay.
The osteoporosis drugs, and then the Ozempics.
Okay, good. But the thing about Ozempic, I remember this study where is it the weight loss or is it the Ozempic, right? There was a study where they looked at gastric bypass in diabetics, and they essentially divided them into 2 groups, where one group got the gastric bypass and the other group got the diet that the gastric bypass patients would have to eat after they had the gastric bypass. They both had the same benefit. Exactly the same weight loss, exactly the same benefits on metabolic health. So is it the surgery or is it the diet? Is it the Ozempic or is it the weight loss? And I think that's important to think about. So just to close, I would love to kind of hear one, what you're most excited about that's coming up in this field, and then two, what your personal regimen is for staying healthy and living a long time, given everything you know.
Okay, so let me tell you, I'm also the scientific director of the American Federation for Aging Research, and I drove three big projects. One is the TAME, so we talked about it. Okay, this is under the umbrella of the American Federation for Aging Research. The second initiative, we kind of talked about it, but it's the SuperAgers initiative. So I have 750 centenarians. Tom Pearls have 1,000 centenarians. It's not enough to do validation and to do discovery. Okay. So we're driving to recruit 10,000 centenarians and one of their offspring and somebody who's married to the offspring. Triple things, because we have to adjust for the diversity of the population. So this is a main thing, and it's important because if you guys, anybody knows of a centenarian, you go to the FAR web and there's the SuperAgers initiative, or you just put SuperAgers initiative. We are sending the to spit the DNA. That's all. It's a genetic study for now, but it's a community. The FAR community is not the sick people; it's the people who live longer and healthier. Okay, so this is a very exciting project. And the third project, it's called FAST. It's about biomarkers, right? And biomarkers is a hot new topic because we have what we call an omic way to look at them. We don't measure one biomarker at a time. We're measuring thousands or maybe 100,000 at a time. And we have a project.
You mean DNA methylation, or are you talking about something else?
So no, everything, proteomic, metabolomic, methylation, everything. And what our strategy is to go to studies that already were completed in the four examples that I gave you: SGLT2, metformin, GLP-1, and get samples of the first year of the study before and after, and do all those omics and discover, first of all, what are the biomarkers for aging? Okay, different ages, what are the biomarkers of aging? Second, what changed specifically after treatment? Some of it will be specific for the drug itself, okay? But then we'll have all studies and we'll ask what commonly changes with aging. Because it's not only, we're pretty good as telling you your biological age. But that's not important enough. We want, if you come to Mark to treatment, we want to show that those biomarkers change. If they don't change, and methylation don't change within a year, okay? Or if ever, or not all of them change. So we want to have biomarkers that you will use, and maybe in 2 months, you would see where the trend is. And for Longevity Biotech Association, not to spend money on phase 3 trial and fail, but get the signals like we get from cholesterol or hemoglobin A1C.
Mm-hmm. So what you're talking about are these sort of intermediate things that are easier to measure than whether you get a heart attack, a stroke, or cancer, or diabetes, or dementia, or death, but that actually correlate with these things. And that are, you're talking about a kind of a network of biomarkers, that not just one, that we're going to be using that reflect a larger pattern of dysfunction or function in the body.
So we're going to look to use 100,000, but we hope that maybe 10 are depicting everything, okay? Or 100. I mean, it'll be, eventually some are going to be enough. We don't want everybody to spend $1,000 per test per patient to figure out what it is. It's not going to be necessary. But we hope to do reduction that is significant.
That would be amazing. It's sort of like the Immunomes project from David Furman, where he looked, found, all the cytokines, and he found 4 that were most highly predictive. And if you just measure those 4, how close are we to that? How close are we to having a true biological age set of biomarkers that we can replicate and use with our patients?
I have an answer. In May. Yeah. As long as you don't ask me the year. May.
Okay, May 2050. Okay.
No. Look, there's a huge progress in the field. Okay, there's a huge progress in the field, but with the progress comes also problems. Okay, comes problems, comes noise. It's people who are, there are three different kind of people involved: the biologists, the doctors, and the computational people who talks different languages. We have committees that are dealing with that. It's not as fast. I call this initiative fast. It's not as fast as I was hoping.
It should be like the Manhattan Project it's so important. I think it's so important.